Hi, this is a calculus video on slope fields, otherwise known as direction fields, and I'm generally following the order of James Stewart's calculus textbook. This is the second section in his chapter 10, which is on differential equations. This section has two parts. Part of it's on slope fields and the other part's on Euler's method. I thought I'd do two separate videos on one on each one. So what's a differential equation? Well, hold that thought if you forgot. First of all, there are lots of general solutions to a differential equation often. So that means that you could plug in a number of different sets of numbers and it would work out. Here's an example of a differential equation. Y prime equals x plus y. What makes it a differential equation is the fact that we have both the function y and the derivative of the function y prime, the first derivative, in the same equation. Now, of course, it could be it could be the second derivative, it could be the third derivative. There are all kinds of different ways that it could be arranged, but a differential equation is basically an equation in which a function and one or more of its derivatives on one level or another are in the same equation. This particular equation, there are lots of possible solutions to this particular set of variables. Now, the idea of a direction field or a slope field is basically you plot a lot of those possible solution points, and at each point, instead of drawing a dot, you draw a teeny tiny little line with the slope, for example, at this one. So you have x and y coordinates, right? And then you have a slope at those x and y coordinates. So for example, let's say that for this particular differential equation, we wanted to know what the slope of a differential equation whose solution goes through 0, 1. What would it be? Well, 0 plus 1 equals 1, so the slope would be 1 at that point. And so you end up with something like this. Now I drew over it with this line here, but basically at 0, 1, the slope is 1. That's like a 45-degree angle right there, and I drew over it with my line. But basically what you can see is that there are each of these slope paths, each of these fields of slope solutions represent a certain solution to the differential equation. So again, in my previous video introducing differential equations, I pointed out how messy these are. They're not nice and neat and formulaic a lot of the time. But what this does is graphically we can draw these little slope, and I've done a horrible job here. I apologize. The picture in the book is better. But the idea is that you can see that there are a number of different solutions that would fit this equation. This one's interesting here, right? That looks to have a slope of -1. And so if we go back to the original equation, and by the way, I gave you an example of a table here. So something with a slope of -1, let's see, -1, 0. I mean 0, -1, yeah. 0, -1 is a solution to this differential equation, and the slope at that point, because 0 plus -1 is going to be -1. And indeed, we have a teeny little line with a slope of -1 at 0, -1. So you see, these are all solutions of particular points that solve the differential equation. And instead of drawing a point, we've drawn a teeny little line with the slope that would be appropriate for that particular point. So this is what a slope field is, or a differential or direction field. Well, there's another example in this section that I thought I would mention. Now, I don't know whether you've had physics yet. When you're watching this video, there's a fair chance that if you're reading this chapter, you're in the second or third semester, probably, maybe beginning of the third semester of calculus, or maybe in the second semester of calculus. And so there's a chance you've had physics by the time you read this chapter, but maybe, I don't know whether you've had physics with calculus at the point. But so this is a circuit. You have circuits in your house. It turns on the light. I could go over, turn off the light here in this room, and I would break the circuit. This represents a switch. It's open right now, so there's no electricity flowing around this circuit. E here stands for, I guess, electromotive force, which is measured in volts. That's like the push for the electrons. And then resistance slows them down because we can't let them be too happy. R stands for resistance. L stands for induction. Now, induction is like a coil, and induction tends to it tends to when you close the circuit, it kind of ramps up and then hits a certain kind of equilibrium. L, and then so I stands for current. I'm not sure why they used I for current, but current is how much electricity is flowing past, per time. So like how many happy electrons are passing this point at any particular point in time. So those are what all these variables stand for. L is for inductance, R is for resistance, I is for current, E is for electromotive force, or which is related to volts, and then di dt is the change in current per time. And when you close this, because there's an inductor in this circuit, when you close it, it's not going to immediately turn on all the way. Because of this inductor, it's going to kind of round up. Okay, so there's a little bit of physics for you fans out there. Now, so the example in this section plugs in some values. So we're told that the power source is a constant 60 volts. Okay, so we can plug in the 60 for the E, the electromotive force. R, we're told, is 12 ohms. That's an omega in Greek, which stands for ohms. So we can plug in the 12 for the R. And then the inductance is 4 henries, named after one of the guys that did a lot of early work with inductors. Okay, so the current is what we don't know. We don't know the current at its equilibrium point, and we don't know the change in current per time as it's ramping up. Now, notice that this is a differential equation, because we have a variable, the current, and then we have its derivative, the change in current per time. Okay, so it's a differential equation. What does the slope field or the direction field look like for this? Well, again, not nearly as well drawn as the book. And by the way, computers do this really well. This is the nice thing about computers, because in the time it takes me to look at my watch, the computer has been working at 186,000 meters per second, the speed of light. And so the computer can do a whole bunch of stuff that would take me a long, long time to do. I'm exaggerating probably a little bit, but not too much. Okay, so you'll notice that when this circuit is turned on at zero time and zero inductance, it goes fast, and then it reaches a kind of equilibrium at 5 henries. Is that right? No, at 5 amps. Sorry, it's the current that's the variable that we don't know. At 5 amps. So once it's reached its full status, then the current going through this circuit is going to be 5 amps. Okay, so this is a slope field, and you can see that this equilibrium point, it levels off at 5 amps. Okay, and it takes it about a second. It looks like it takes it about a second for it to reach that particular point. Okay, so that's a slope field. It's a way of using graphics and graphing to solve differential equations. So, final points. As I just said, since the limit as t approaches infinity of the current is 5 amps, then 5 is an equilibrium solution to this. Remember, equilibrium solutions are from the previous video. That's where it equals 0. And you can see it equals 0, right? If we go back to the equation, let's see, if I equals 5, then there's no change. So if I equals 5, then this equals 60, which means this has to equal 0, right, for it to work, which means it has to stop changing. And so the change in current per time goes to 0 at 5. 5 is an equilibrium solution. Time, by the way, is an independent variable here. It doesn't appear on the right side of the equation. If we take this di dt and we put everything else on the other side, di dt equals, we're going to divide everything by 4, so it's going to be di dt equals 15 minus 3i. And so 15 minus 3i, that's going to be on this side of the equation, time doesn't appear on the right side of the equation. So it's an independent variable, which means the equation is going to function regardless of the time. And so we call that kind of an equation a autonomous equation, because the time doesn't affect what it does. In fact, what you may notice that the slope for any y coordinate in this, and I didn't draw it very well, but the slope for all y coordinates, so whether it be y equals 2 or y equals 4 or y equals 6, you'll notice that they have the same slope. Every y coordinate has this, every slash has the same slope at that particular point. And so the slope for any y coordinate is the same across in that kind of a case when the equation is autonomous, because time is not part of the right side of the equation. Okay, well, that was my feeble attempt at direction, slope fields or direction fields. Thank you.